Today we're going to be graphing logarithm functions, and you need to understand what a logarithm is. Remember, it's an exponent. So let's talk about some different values that you're going to be picking for x, and it's going to be different for every log function. What you want to be picking for x is powers of -3. So think about it like this. You want to be picking powers of -3. Or I'm sorry, of 3. You want to be picking powers of 3. 1 power of 3 is 9. Okay, when you plug in that for x, 3 to what power gets me 9? That's going to be the second power. You could pick 3. 3 to what power gets me back 3? That's the first. Plug in 1. 3 to what power gets me back 1? Well, that's going to be 0. Now the next are slightly more complicated. 1/3 is technically a power of 3. So what you could do is you could look at it like that, and then when you plug in 1/3 for x, you get -1. Okay? When I plug in 1/9 for x, I get -2. Honestly, what you could also do is you could look at it like this. Okay? Plug in known things there that you know for y. Okay? Notice how these points are very common values that we've been picking for x. Typically when we've been graphing. We use these values when we graphed an exponential. The reason that the x's and the y's switched when we were graphing, say, an exponential function of 3 to the y equals x, which is this converted to an exponential, the reason these values look so familiar is because logarithms and exponentials are inverses of each other. Okay? So if you want to convert it to a exponential, you're going to be picking values of y. So you're going to be picking values of y and then getting your x's out. Okay, so let's graph these points. Okay, I have x is 9, y is 2. We have when x is 3, y is 1. 1 and 0. And then for these, again, you just have to approximate them. It's okay if they're not perfect. Okay, so now that's what our graph looks like. Okay, remember, logs and exponentials are inverses of each other. So whereas our domain for our exponential was all real numbers, our range now becomes all real numbers. We have an asymptote in here. Remember, for exponentials, the y-axis, the x-axis was our asymptote. Now it's going to change to the y-axis. So it's going to be x is greater than 0, and our asymptote is x equals 0. Okay? So that's what your logarithm looks like with your base greater than 1. Now let's do an example where our base is a fraction. And this one kind of looks kind of awkward, but I think it's going to be easier for you guys to plot this one. We have an x and we have a y. So let's pick powers of 1/4. Okay? So what powers could I have of 1/4? If you plug in 16 for x, you're going to get -2 out. If you plug in 4 for x, we get -1 out. When you plug in 1, we get 0. When we plug in 1/4, we get 1. And when I plug in 1/16, we get 2. So again, if you're more comfortable, convert this to an exponential. 1/4 to the y equals x, and then pick x values, pick y values that are going to get you out your x values. Okay, this doesn't have any translations left and right. We haven't even talked about those yet. So your asymptote is still that y-axis, or the line x equals 0. And I think of that asymptote kind of like a wall that we can't cross over. We're never going to cross over that asymptote. Okay? X is greater than 0. Okay? A logarithm, this value is never going to be negative. Because if you think about it, okay, that's what the x equals when you're taking something to a power. When you're taking a base to a power, you're never going to have a negative number. Our range is all real numbers. Okay, so plotting these points. I know this 16 and -2 is going to be challenging for us to plot, but I'm just going to get us an approximate over here. 4 and -1. 1, 0, 1/4 and 1, and 1/16. Notice how that's real small. So your graph then comes down and looks something like that. Okay, so that's an idea of what your graph looks like. And I know that kind of looks like an exponential, but that is actually what a logarithm graph looks like. Okay, please make sure you guys have this in your notes. Hey, so your parent function, log base b of x, you have two different types. This is if your base is greater than 1, so 2, 3, 4, 5, anything like that. And then your graph looks like this if your base is some sort of fraction. These are the key points that you guys want to have that you want to be translating. Okay, it's always 1 over your base and -1, 1 and 0, and your base and 1. Okay, notice how those are the same points here, just they're in different locations. Your domain is all positive real numbers, or x is greater than 0. Your asymptote is the x-axis, or x equals 0. Your graph is continuous and 1 to 1, so I can find the inverse of it. And remember, inverse is an exponential. Your range is all real numbers. And then we have our x-intercept is 1, 0. And that's always the same unless we have translations. Now our translations, okay, these are the translations that we've been doing. So whenever I'm adding or subtracting something to the x, you're going to be moving left and right. What the number you see being added out of the log function, that's going to tell you up and down. A is going to tell us whether it's a stretch vertically or compression vertically, and if A is less than 0, we're going to reflect across the x-axis. Okay? Again, as a reminder, domain x minus h has to be greater than 0. So therefore, x has to be greater than h. Your range is always all real numbers, and your asymptote is the value that makes this 0, so that's x equals h. So that's an easy way for you guys to find domain, range, and asymptote. Okay, first example with a lot of translations going on here. And I used my calculator to get some of the points. We always start with an x, and then for your y, get a graph that's non-translated. So take away the +4, the -5, and the 1/3. So we're going to look at getting our points, log base 6 of x. Every graph is different, okay? It all depends on what that base is. So let's look at powers of 6. Well, I could have 1 over 36. If I plug in 1 over 36 for x, that's going to get me out a y of -2. If I plug in 1/6 for x, that's the power of -1. 1 and 0, that's going to be consistent, and then we're going to translate that point. When I plug in 6, we get 1 out, and then when I plug in 36 for x, we get 2 as an output for y. Now let's talk about our translations that happen here. Okay. The +4, remember that shifts it opposite of what it seems, so it is going to shift us left 4. Okay, so I'm going to subtract 4 from all of these values. And again, I used my calculator to get these values. Especially with these fractions. Okay, so that's that piece. Now, your y's. You have 1/3 times the whole thing. That's your a. So I have 1/3 times y minus 5. And again, I used my calculator to get these numbers. And what I'm doing is I'm plugging in these y values for y and calculating it out. Remember, I took and I plugged in these values for x and calculated out. Okay, so our asymptote is the value that makes this piece equal 0. So that's x equals -4. Your range is always all real numbers. Your domain, x plus 4 has to be greater than 0, so x has to be greater than -4. Okay, this grid isn't right. I need to move my y-axis over. So I'll do that here, and then I'll continue. Okay, so I moved my y-axis over a little bit because my asymptote is x equals -4. So I'm going to draw that in. And you want to, again, keep in mind, I always think of that as a wall we're never going to cross. It's a wall that we end up never crossing. And the domain is x is greater than -4, so it's going to be all these values here. So now just start plotting the two far columns versus each other. So -3.9. So that's almost 4, -5.6. And the next point, these points are semi-close to each other because we have this compression of 1/3. So we're about right there. Now I'm at -2, -5. And I'm at +2, -4.6. And then I'm at 32 and 4.3. And I'm just approximating that. It gets you a general idea of what your curve should look like. And that's what your curve should look like. Okay? These points were super challenging because our base was so big. I'm going to try and make the bases not as big. Okay? But it gets you a general idea of what our curve is going to look like. Okay, next example where we have our base being 1/3. Again, remember that the original points that you're picking for the y here, take away all your translations, and we just have y equals log 1/3 of x. So if you prefer to write this as an exponential, so 1/3 to the y equals x, pick easy values for y. Pick -2, -1, 0, 1, and 2, and plug in those values for y. That's going to get me 9, 3, 1, 1/3, and 1/9. Okay, now let's go with our translations. Let me erase so that I can see what my actual translations were. Okay, so x minus 3 shifts everything to the right 3. So I'm going to add 3 units. That gets me my asymptote, x equals 3. X has to be greater than 3, and then our range. So I get these values. And I could do these without a calculator, because this is an easier base for us to do. Now, the translation on your y, we have 2, vertical stretch of 2, y, plus 4. Now I'm plugging in these y values into that equation to get my y values. So I get 0, 2, 4, 6, and 8. Now again, you're plotting the far columns versus each other. Twelve, 0, 6, 6 and 2, 4, and 4, and then 3 and 1/3. Let's put in our asymptote so we don't cross that wall. 1, 2, 3. Okay, so let's keep in mind that that's a wall we're never going to cross. Okay, that's our barrier. And then approximating these last two values, so we have 6 and 3 and 1/3, and then 8. And it looks something like that. So that's again what our graph looks like when your base is a fraction. Okay, our next example. At Earth's surface, the air pressure is defined as 1 atmosphere. Pressure decreased by about 20% for each mile of altitude. Atmospheric pressure can be modeled by this equation. So pressure is equal to 0.8 to the x power, where x is altitude in miles. Find the atmospheric pressure in atmospheres at an altitude of 8 miles. Well, altitude, x, is what your altitude is. So all you're doing is plugging in 8 for x. When I find that, I get 0.168. Now, units is atmospheres. They tell me my units. Okay. Now write the equation of the inverse of the function. Okay. So our original function is this. We switch x and our y variable, which is p. Now our inverse, how do I break down this p from our exponent? That's your logarithm. Okay, so I have log base 0.8 of x is equal to p. But let's make a little notation that that's our inverse. Okay, so this is our inverse. Again, realizing that logs and exponentials are inverses of each other. They undo each other. Okay, I think this is a challenging video. Please, if you didn't understand, go back and rewatch. State the translations of the function. I'll give you a hint. There's more than one translation of that function. And then in your notes, try and get me a graph of that function. I'm not going to give you guys credit on the notes if you don't have a graph of the function sitting there. Okay? And please make sure that you get these translations and your lesson summary in on time.